Hello chemists! This is Ivan and he's going to describe a chemical reaction for you. This is an example of a double displacement reaction. In here we got lead chloride, which is a solid, and sodium fluoride, which is an aqueous. So here's what we do. Imagine this is A, this is B, this is C, and this is D, okay? Now, what we do in a double displacement reaction, we put A with D plus C with B, okay? Now, so A is lead and D is fluoride. But since we know that the charge on lead is 2, because we need 2 chlorines to balance it out, so it's plus 1, and then, my bad, minus 1, and then plus 2. Therefore, we need 2 fluorines to balance out the lead. So it would be PbF2. What's the state on this?
Solid.
Solid. Is it solid?
Yeah.
You sure?
Yeah.
Which is a solid plus what? NaCl, which is aqueous. Now, after this, what we do, because solids and liquids and gases cannot be separated, so we would break down the aqueous stuff into its ions. So we would break this up when writing the whole complete ionic equation. We would rewrite. This would be the same. This would change into. Okay, you also gotta balance the thing. I forgot to balance it, but you gotta balance it. So here, wait, hold on. We got NaF. So you gotta balance it. So there's F here. There's 2 F's here. There's 1 F here. So we put a 2 here. And then we put a 2 here because there's 2 NAs, and then we have 1 here, so you got 2 right here, and then now there's 2 Cl2s and there's 2 Cl2s. Bam! After, what you do is now you gotta break this thing into ions because it's an aqueous thing. You only break aqueous stuff into ions because aqueous, it has a hard time, it's easily dissolved in water, which is why it breaks apart. Then, you break this up into, and you got to make sure you write it like this: 2 Na plus, one arrow, 2 F minus. Okay? You can put AQ at the end of both of them. And then same thing, you will go to the reactant side here, and you break this up as well into 2 Na plus AQ plus 2Cl minus AQ. You can put AQ at the end of both of them. I just didn't put it because it's just extra work. And then we'll look at it. What goes into the actual reaction? The Na would cancel out on both sides, and that's actually the only thing that's canceled out. So, because the chlorine is connected to the lead here, and we can't break it apart. Therefore, the Na, bam, it's gone. It's gone, and it's gone on this side. And then whatever is not gone is our complete net ionic reaction, which would be the PbCl2 solid plus 2F aqueous equals PbF2 solid plus 2Cl aqueous. And you got to make sure you don't write the minus in the net ionic equation. You only write it in the complete ionic to show the charges. Voila. Did I forget anything? Think I got it? Here's one thing to watch out for. Now I'm going to go really fast over a single displacement. With single displacement, if you have, I don't know, CUS plus ZN, what goes to ZN?
CL.
ZnCl, I don't know. You gotta make sure there's gonna be chart. There's gonna be chart on your. You should be given a chart, and it's usually, it's gonna have an up arrow on it, and it's gonna be, the arrow. The higher the arrow, the higher an element is on the list, the higher the reactivity. So, if we have Cu right here, but Zn is here, the reaction cannot happen. It will not happen because Cu is a pussy boy. It cannot replace the Zn because it's more powerful. But however, if the reaction was ZnCu, then it can happen, and then we'll just get the ZnCl plus Cu solid. That's disgusting handwriting. But you get ZnCl, I don't know what it makes, I'm not going to your states, and then Cu solid, because it would just knock out the copper from the Cl because it's more powerful than him, according to the chart that we are provided. So that's signal displacement. And now that's one thing you gotta watch out for. So remember, if it's more powerful, then the reaction can occur. But if it's less on that thing, you just write no reaction. There's not gonna be a reaction. Remember, you cannot separate water, liquids, anything with L and then S, no separation. With aqueous, okay, you can separate that thing. The way I remember it, aqueous is made of 2 letters. Bam! You can cut them in half. You can't cut the letter in half here. That's why you can cut an 8 in Q. Plus, I mean, the reason behind it is because the water can dissolve it easily.
And gases.
Yeah, and gases. You cannot bring gas. It doesn't cut in half. It's a letter. Lastly, let's go over oxidation reactions. So we have a good example. Cu plus, give me something. Hold on. Stay right there, chemists. I'll be right back. I remember when I was learning this, I had to have a Google, like a Google Doc on it. And I had examples here. Give me 1 second, chemists. Loaded. How long has it been already?
Does it say?
Bum bum. No, it does not. What was it? Oxy. Yes, there it is. My Google Doc. Alright. So for example, we have okay. I'll give you a hard one. We'll start off with just oxidation number. So we have I'm just reading through my notes. Alright, we have potassium, hydrogen, and CO3 all linked up. Now, the rule is, if there's no fluorine present, the O3, the oxygen is going to be -2. And then, hydrogen is +1. And the way, now we just make an equation. Hold on, I'm forgetting something. Okay, here's what I forget. The things in the first column are usually going to have their own oxidation number because they're charged. Because of the fact that they're not as electronegative. So they don't have to compete with anyone. So this one's going to be +1 on average. And now we just make an equation. Because the goal is to be at 0. So we just make an equation. It will be +1 +1 -6 plus x. And then we solve it, which would be 6 equals 2 plus x, x equals 4. Therefore, C equals 4. Is that a pretty good explanation?
Yeah, just it would equal 0 if the whole compound is neutral.
Yeah, so it would equal 0 if the whole compound is neutral, but if this thing was minus 2 right here, if it had a charge, for example, we have, so if this was negative, we would just put negative 2 as our final destination. Now, as regarding for a reaction, things you gotta watch out for. These are words of wisdom. If it's a solid, so for example, if we have an element alone, Cu, or like H2, whatever, doesn't mean anything. It doesn't mean anything. It doesn't count. It's gonna have a 0. Oxidation number is 0. However, if in the end reaction, this thing, the charge goes from a 0 to a -1 or something, then it did something. Now, again, you write the reaction, you figure out the oxidation number, just like we did above for everything. And if the number goes down, so if it goes from if it goes -1 to -3, it's reduced, right? And that's an oxidizing agent, right?
Yeah.
So, I haven't looked at this in years, in like 3 months. So it's a reduced, and it's an oxidizing agent. How did teachers do this, man? Agent. Now, if it goes up, and it goes from 1 to 3, it's oxidized, and it's a reducing agent. So it's oxed, and it's a reduced Ag. Let me go over one more example, how to calculate the oxidation number. Just one more. Last one from the chemists.